In this video, we will present our recent work, Constrained Passive Interaction Control, leveraging passivity and safety for robot manipulators. We will first introduce the background of this work, and then we will give a formal problem statement. Then we will introduce the novel approach that we proposed. At last, we will give some experimental results to verify the effectiveness of this work. Our work is based on the dynamical systems interactive motion planning approach. Here, our agent will move along with the vector field, in other words, a virtual dynamical system. The basic idea is that the velocity of every point in the state space is defined, and the agent will converge to some certain points eventually. We could predefine this dynamical system just using the gradient of a simple Lyapunov function, or it can be learned from demonstration using some statistical models like Gaussian mixture model, Gaussian process, or neural network. Once we have the high-level motion planner, we aim to design a passive torque controller for motion actuator. Passivity means that for a specific system, the input energy power is greater than the storage energy power. In the sense of passive manipulator control, passivity makes the robot allows external perturbation when executing the tasks. So our target is first, the passivity should be preserved, and second, the robot should move along with Fx and dissipate energy perpendicular to Fx. So once we make the assumption that the ds is conservative and we select the input-output pair and the energy storage function, then if we carefully design the D matrix with gravity compensation, the controller will be passive. However, this controller has no explicit safety guarantees like collisions, joint limits, etc. And in the control field, the control barrier functions is proposed to get a safe control law. If we define a scalar barrier function h of x, the invariant set, or the so-called safe set, is the set of x which makes the barrier function positive. And this theorem tells us that the existence of a control which makes the time derivative of h greater than alpha h is necessary and sufficient condition of set invariance. Generally, people use this condition as a constraint of a QP, which finds a U which is closest to the reference U subject to this constraint. However, for force robot control specifically, if our invariant set is defined in position level and the control is in torque or acceleration level, this CBF is not enough, since the control term will not appear if we just take the first derivative of h. This means that if the CBF has relative degree of 2, we will need to use this exponential CBF to guarantee safe invariance. There are some conditions of K1 and K2 to design the eCBF. Once we have those background, we can state the problem that we are tackling. The objective of our torque controller is in task space, which is 1, tracking a conservative virtual dynamic system, and 2, preserve passivity. And then we want the controller to have some safety constraints in joint space. Here we consider 4 safety constraints that are joint limits, self-collision, external object collision, and singularity avoidance. So this is the general framework of our controller. We use quadratic programming to compute the control law. This is obviously convex and can be solved in real time. For the constraints formulation, we aim to define different barrier functions for different safety guarantees. Once we defined the barrier functions following the procedure of eCBF we talked before, we can easily formulate the convex constraints. Also, we define the first 2 constraints as hard constraints and cannot be violated at all the time, and the last 2 constraints as soft constraints. So in this QP, we also add select variables to the constraints of external collision avoidance and singularity avoidance. Next, we will focus on how we obtain those barrier functions. For self-collision avoidance constraints, since the shape of the surface of the manipulator is complicated and it's hard to define the joint space boundary analytically, we use a data-driven function to represent the self-collision boundary. Here we choose a multi-layer perception model and treat the problem as a classification problem. We randomly sample different configurations in joint space and their labels of whether self-collided or not as the data set. Then we train the model, and the output has 2 neurons, which are gamma 1 and gamma 2. Generally, if gamma 1 is greater than gamma 2, the prediction result is free configuration and vice versa, which is collision configuration. So we treat Q such that gamma Q function is equal to 0 to be the self-collision boundary. This model is actually accurate since the prediction accuracy is above 96%. For the external object collision avoidance, we adopt the joint space sign distance function proposed in this paper. This function gives us the minimal distance between a quarry point in 3D space and each link of the robot. They also use the neural network models to fit this sign distance function. Basically, if the value of this function is 0, it means that our quarry point is exactly on the surface of the robot, and if it's greater than 0, the point is outside the manipulator, which indicates collision-free. The last two barrier functions are given analytically, which are joint limits and singularity. For joint limit, it's quite straightforward, and for singularity avoidance, we use the manipulability index to measure the distance between the current configuration and the singular configurations. At last, we will show some experimental results. This is a simulation that shows self-collision avoidance. If the task space DS motion plan leads the robot to self-collision, our constraint controller avoids it. On the left, even if the target is inside the robot, our controller still tries to avoid the self-collision. On the right, we could show the external collision avoidance of our controller. This simulation shows all the constraints activated, and our controller can ensure the satisfaction of multiple constraints. Then we did some hardware experiments. We can see the robot avoids self-collision with no external perturbations. And even with external perturbation, the robot can still avoid self-collision. At last, this experiment shows the external collision was subject to external perturbations. Here, the head of the tripod is considered as an obstacle.